Hi, my name is James Ammon, and I'm a protocol engineer over here at Constellation Labs. And today, I'm going to be doing a build session with you for a little to-do application that will really showcase how to build on the Metagraph framework for the Constellation Network. So the goal of this whole video today will really be to explore the nitty-gritty of what's involved in building an application. We'll explore the combiner functions and the validations and really try to develop a solid foundation to give you as a developer the tools needed to start building and leveraging, on the Constellation Network and leveraging our secure and scalable architecture. All of the code today is available on our GitHub under the Metagraph examples, and we're even going to be going commit by commit, and I'll be showing you everything you need to follow along, and I encourage you to do so. I just mentioned the combiner functions and the validation lifecycle, but maybe it's kind of unclear how that actually works in practice. And so here's a really simple diagram to kind of outline what I mean by that. And so here we should look at first. Let's look at on the left side. And we see that time is progressing as we go from the top down, right? And so we see the different stages of how data might be generated and ingested into the system. First, there's collection and transmission and signing and transmission. And that is done by, non-verified and untrusted edge nodes. And those are things that are like your data sources. Really, while they're still signing it, they're not leaving a trail of the data. They're not necessarily leaving a trail of data they're generating over time. But those edge devices and those signatures are then pushed one layer into the system to the data L1 nodes. And these are the non-verifiable but semi-trusted nodes. So again, they don't leave necessarily the data L1 nodes themselves maintain a trail of the data that comes in, but they are still a provisioned environment, and they're identifiable. And the purview of these data L1 nodes is to perform the first level of validation. And I like to think of that validation as happening on the Metagraph public data. So the entire Metagraph state that's been accumulated over time, but a portion of that state is sectioned to be in the public domain, and while another portion it can be sectioned to be in the private domain. And we'll really get into what that means when we look at some code. But once those data L1 nodes perform that first level of validation, they go about the gossiping, and the block proposal is all taken care of by the framework. But that happens, and those transactions are packaged and then sent one layer deeper to the Metagraph L0 nodes. And so these Metagraph L0 nodes really are our first step of the data lifecycle, where a trail of the data, like a chain, is made in time. Much like a typical blockchain. And again, validation happens at this layer. This validation happens can use both the public and the private data. If the data has been verified and validated as true, accumulated into the Metagraph state via the combiner functions, and then packaged into a snapshot, a Metagraph snapshot, or also you might see it referred to as a currency snapshot. But those snapshots are then signed by the different Metagraph L0 nodes. Again, those permissioned and privileged nodes of the network, those trusted nodes, and then they send to the lowest level, the global L0 network. And this global network again maintains a verifiable trail of all the data over time. So this is again like another blockchain, but there's many chains that can feed into this like bigger global chain, and that's where the whole idea of the DAG and like why we call them metagraphs. But then your data gets I say that the data is untrusted, or not the data is untrusted, but those nodes are considered untrusted only in the sense that anybody can become a member of that network. And so you don't necessarily need, as the Metagraph developer, to trust those nodes, because you've already gone through the multiple levels of verification down to this untrusted source. That doesn't mean that it's not verifiable or there's not an audit trail. It's much like you can think of the Bitcoin network, that everything is from Genesis verified from the Genesis point up. But here, another way of thinking about how the data life cycle progresses over time is how from each layer in the network, as we progress, kind of like, through an onion, right? That's the other way I like to think about this, is that on the outer edge, it's really your most, where data is most subject to change or most subject to like churn. And as data gets slowly verified and undergoes the different levels of validation, the reliability of that data is increasing over time. So when data finally gets to the global L0, it has the most reliability. You can trust that data. And so you can use that, anything that ends up on the global L0, like as a source for making other automated decisions or integrating with other metagraphs, which is really one of the big powers of the Constellation Metagraph system. So, for some more detail on that, I'm going to refer you to our documentation, as well as the previous video in this webinar series, where Ryle and Marcus spend some time really going through some of the theoretical underpinnings of the Metagraph networks. So we're going to move on, and let's talk about what we're going to actually do in this tutorial today. So I've tried to break up the different steps of the code we're going to look at into all the different commits, and you can see from the GitHub link that provided earlier in the presentation where these commits reside. But we're really going to go through the step by step, all the different, how you develop a metagraph over time. So the first thing we're going to do is we're going to look at the code, kind of the basic framework and some sensible defaults. So metagraphs are incredibly customizable, and honestly, the customizability for someone who's just looking to get something going might be a little overwhelming at first. And so that's why I say we're going to start with some sensible defaults. We'll make decisions on how to do serialization and how to do some of the lifecycle methods. And so we're going to walk through what that framework built up around this example will look like. So then the next thing that needs to be decided for application developers is the schema design, right? What are you trying to do with your application? In this example, we're going to be looking at a to-do application, just a simple, Jira-like application where tasks can be created and then they can progress through time until they're closed and then archived, right? And there can be different statuses on the tasks and due dates attached to it. But that whole application design it really starts at the data. So what is the data that you want to exist in your application? And there are two types of data that we're going to really be concerned with, kind of your state and the transactions. So in more traditional database terms, you might think about as that, what is your table design? And then what is your updates? What are your modifications to that table? How do you ingest data? So that's going to be step 2. And then step 3 is where we really get into the meat and potatoes of the metagraph, right? We take that idea from step 2, the state and the transactions, and we decide how we're going to combine those transactions and into the state over time. So how do we accumulate state? How do we build it up over time? Which great thing about blockchains is that you can build that state, and there's a reproducible, verifiable trail of every version of that state over time. And so the functional definition of how you do it is a thing we call a combiner. And so within step 3, the first thing we're going to do is the combiner is important enough that it'll get its own commit. And so we're going to look at that for this little to-do application. And then in the next step, we're going to define the individual validation rules. So we'll see in the combiner that it's kind of easiest if we just think about how to accumulate the updates into the state. But maybe we want some guarantees about the certain properties of those updates, right? We don't want fields to conflict or something like this. But the enforcement of that shouldn't happen at the combiner function. It makes things a little too complicated. So instead, we can define rules, like form validation rules. And so what we'll do is we'll define like the independent rules first. That's in step 3.2. And then we'll go on in step 3.3 to actually combine those rules into complete update validations. And updates are just the term we use for the transactions that are generated and contain data that then gets put into the state over time. And so after that, you really do kind of have a functioning metagraph once you're able to define the data schema and the state and the updates. You define how those updates accumulate into the state over time, and then you define the rules around what is a valid update. That kind of is most of the metagraph. But the real, again, one of the powerful things about our framework is that we can support even more advanced things like creating customized API endpoints. So imagine a smart contract, but that has REST endpoints to it, right? So that's one of the great things that Metagraphs lets you do. So we'll see how to integrate those into our application. And finally, the last bit of code we'll look at are how we can do the even more application development and more integrations with Web 2.0 services via daemons and application configuration, which really gives you a lot of power to develop a metagraph in a way that really suits whatever your business logic might be. And finally, we'll spin up our little to-do application and do some testing in a couple different ways. To go over the specifics of it, how we're going to do our testing. First, we'll look at some really simple get routes through a browser, how you can just present data. Then we'll look at a Postman collection, which will also be included, or which is also included in the repository for looking at some hard-coded examples. And finally, there's also, again, once more, there's scripts included in the repository for generating interactive examples. So you can, add in your own data and send it to the to-do application, and we'll see how that functions and how we can actually, change the state and make sure it behaves in the way that we'll define later on in the application. A couple of things that we're not going to cover in our little build session today are rewards transactions. So how do you, give people tokens that for participating or sending data into the metagraph? And we also won't be considering transaction fees. So these are both topics that if you're interested or if you need to include them into your application framework, I'd highly recommend to go look at the docs at the link here. And there's lots of information, and even some of the other examples integrate the rewards transactions and the transaction fees. Okay, so with that, I think we're gonna hop over to some code and really get into the development.
All right, so here we are. We're in our little to-do project, and as you can see, I have some files over here on the right, and we'll just go ahead and look at the commit tree. You can see we're currently on step 1, the initial setup. So if you'd like to check out that commit and follow along, that's where we're going to start. We're going to start to delve into it. So first thing I want to point out is, there's a bunch of stuff in here, things like the build SBT that defines the structure of the whole project, and there's the dependencies, and by sensible defaults, a lot of that stuff is try to be taken care of for you. And we're going to really be concerned about what's under this modules folder, and in particular, we're going to be concerned about the files in this data L1, this L0, and in this shared data folder. So the shared data is really just things that are common between this L0 and the data L1, whereas the L0 is that metagraph L0 that I showed earlier in the presentation, and the data L1 is that first layer validation, and then it forwards data onto the metagraph L0, which does the further validation and the combination and so on and so forth. But some of the things that we'll notice in here is if we look under lifecycle and lib and app, we got a whole bunch of things in here. And so app is really that application config. So we'll come back to that in a little bit. And schema has a couple of things. And so that's what we're going to look at in the in step 3. And so step 2 is actually, or I'm sorry, in step 2 for the schema. And then in step 3 is where we'll actually look at some of this lifecycle stuff. So for now, what I want to do is we're just going to briefly touch on what some of this stuff in the lib package, and as well as the metagraph L0 here and the data L1. Now, very, very common structure that I follow in this tutorial is the main is our primary entry point into the application. And so we see here that when the first thing we really have to do is build this thing called a data application. And this might look like a bit of a wild structure, but most of these things are again, sensible defaults that are usable as a starting point to get functionality like the hashing, as well as JSON serialization for saving data to disk and such. And then really what we want to look at is this data L1 service. So we'll hop right into that. The data L1 service we see has a make function, which just makes this thing called a validator, which we'll come back to, and then it calls this base application L1 service here. So let's just look at the structure of the L1 application service. And we do that by this. Okay. And so there's a lot of functions here, but the great thing is most of these things can be, again, considered as sensible defaults, right? So basically everything I've just highlighted, and then unhighlighted, all of this stuff can be taken kind of as a given if you want to just start from a solid foundation and just follow along with the tutorial. So we won't really go into what any of this stuff is, but this modification of some of this functionality is where some of the flexibility in the Metagraph framework comes. So instead, we're going to really be focused on, in the data L1, on these four functions. And furthermore, we get to see that 2 of these functions are just kind of an artifact of the structure of how things are at the moment. And so the data L1 we can kind of ignore this combine function and this validate data. These functions are really only useful in the ML0 service. But given how I've structured this application, we have to give them implementations. But again, for the quote unquote sensible defaults, you can take these simple implementations and move forward. What we're going to have to look at a little bit later is what this validate update function is. And here you can see I've actually just put some question marks, as well as this routes function, which it does have an implementation, but if we just hop to it really quick, we see that right now our implementation is empty. So in the data L1, these will be the 2 things that we'll really focus on providing implementations for, whereas in the ML0, we can hop to its main function. And again, we see a lot of the same or a lot of similar things for creating the data application. Many of these things are just usable out of the box things. And what we really are concerned with is this ML0 service. So let's hop to that. And let's collapse it. And we see again, we have a simple make function, which creates a thing called a checkpoint service and a combiner and a validator. And we'll come back to the combiners and validators. Right now, they're just kind of blank implementations. They're not really useful. And this checkpoint service is a structure for saving data into the state, but can be considered just a sensible default at the moment. And finally, let's expand the ML0 just a touch, as we did before. And we see a lot of similar functionality because again, just given the structure of how I've created this application and split the 2 services. But as I previously stated, this pretty much everything from hash calculated state, set calculated state, get calculated state, all of this stuff, everything I've just highlighted can be used as a starting point, given the structure that's currently in the rest of the metagraph. So we won't really be concerned with modifying any of this stuff today. But the things we'll look at are the validate data functionality, which in this case is just going to be our little question marks, because we're going to come back to how we actually implement it. And we'll also look at the combine functionality, which again, we'll have to come back to what the implementation looks like. So, in comparison to the data L1, let's go ahead and throw them next to one another. And we'll close this for a minute. We see that whereas in the data L1 here on the left, the combine function is really just a simple implementation that doesn't really do anything, right? There's no action that it happens. It just returns its argument. So the combine function and the validate data methods are not ever invoked or not ever really used on the data L1. Conversely, while the validate data is, therefore the question marks. Conversely, on the ML0, the validate update function is not really invoked. So we provide like a default implementation here, but the ML0 does invoke the validate data and the combine functions, thus the question marks here. So that's just a little bit of insight into why this application is structured the way it's structured. You may see other examples that don't necessarily make this split. I find it a little easier to do so. Lastly, we'll look at the ML0 public routes, and we see that for now they're just empty, so we won't be concerned with them. So now that we've gone over a little bit of the data L1 service and the ML0 service, which are the big two definitions for the two different applications, we see there's a couple of other things like we've already looked at custom routes here, but there's also this node context, which is, again, there's a lot of code here, but it can be used straight out of the box. And then also the only thing we haven't looked at here is this data L1 validator. And right now it's just some question marks, and we will come back to this in a later step. Similarly, we've looked at the main here. We've looked at this custom routes, it's just empty. The ML0 node context also enriches some functionality within the application, but can just be used as is out of the box. So we won't really concern ourselves with it. We've gone over the ML0 service, and the ML0 validator is something we will come back to in a later step. Now, you see there's some other things here that, again, can be used kind of straight out of the box. So we have some functionality that just lets us get things like counting updates out of a currency snapshot and getting the blocks out of them. We have a service known as a checkpoint service, which really is just a way, again, to tie an ordinal and a piece of state together for recalling within the Metagraph application. We have we use a library called Circe, which is just a JSON library. And so this is a kind of a default implementation that won't need to change for our example here, as it just provides some needed implicits for use throughout the application. We also have these ordered ops, which is something we'll come back to when we define our schema a little bit later. One big thing that has to be considered when you're building the Metagraph is how do you want to save your data to disk, right? Disks, when you save data to disk, you really need an array of bytes. And so how do we take our in-memory objects and convert them to an array of bytes? And for our sensible default that we'll be moving forward with, we're just going to use a JSON serializer. So we will go from the in-memory object to a JSON representation, and then we will use this printer to turn that into an array of bytes as defined here. Now, again, this is all kind of maybe a little far-fetched. A lot of this can just be used straight out of the box. I'm going through it just for the sake of completeness, but that the reason is here is so that it kind of gives you the leg up and a good starting point. So then things like this latest update validator is really an enrichment function. So we will create an instance of, or we use the latest update validator in some places, but it provides some just nice, some quality of life things. So it's just kind of a Scala-esque way of doing some quality of life improvements within the application. Similar with this signed update reducer, we have a really nice implementation here that's kind of looks imposing when you first look at it, but it really is just a nice like Scala-esque quality of life way of doing things that we'll see how it works a little bit later on. And then our validators use this abstract trait called an update validator. Again, no need to change anything here as it's fine as is. And then the only thing we haven't looked at are these public routes, which will be if we looked at the ML0 custom routes and the data L1 custom routes, they both inherit from this Metagraph public routes, which just sets some functionality for how to actually build the public routes. What we're going to do in the next couple steps, for step 2, we are going to look at our calculated state and our on-chain state. So if I refer later or throughout this tutorial, if I refer to public data, that is what I mean by, or what I mean by that is the definition of on-chain data. So on-chain is the representation of state that actually gets pushed to the global L0 layer. And so here you see we need a definition of the genesis of that state, as well as the form of it. Right now it's just an empty class, and so we have no on-chain state. Similarly, the calculated state is also just going to be empty for now, and we need to define a genesis of it. But the calculated state is what I might refer to as private state. So the calculated state only resides and is only accessible by the ML0 nodes. So if we hop back to the ML0 service, we see that our little checkpoint service thing here actually checkpoints calculated state. And whereas if we jump back to the data L1 service, we don't need a checkpointer, and the calculated state is not used by, it's not accessible by the data L1 because the ML0 is the application that actually takes care of advancing the state over time and needs to track it. And so this calculated state object is only accessible by the ML0 nodes, and therefore why I refer to it as private data. And then in the schema of our objects, we are going to have to define our different to-do transactions or to-do updates. And right now I just have a simple empty class. So we'll change this in our next step. But we do need to extend, we need to inherit from a higher trait up here. And so just to make things compile, we have an empty class here that we'll revisit very shortly. Last thing we'll look at is the kind of the heart, the meat and potatoes, as I referred to it earlier, is our combiner function. And so the state update combiner is going to be where we actually define our insert, how we insert transactions, or how we insert signed transactions into our state, into our data state. And the data state is the complete encapsulation of both the on-chain and calculated state. And so this insert, like here, this method is where we define how transactions get inserted into the data state. And then validator rules is where it's just an empty object for now. It's going to be where we define our different validators, our validator rules, and then we will those independent rules that I was talking about before. And then within each application, so within the data L1, we'll have the validator that I showed before that will define the validations of that actually verify an individual update. So given an individual update and the state of the chain, in the data L1's case, it is the on-chain state. What is a valid update compared to that state? And conversely, for the ML0, we'll also define that verification function, but the ML0 gets to have a little bit more rich context, and so it considers what is a valid signed transaction given the complete data state of a chain, and the complete data state being, again, this combination of the public on-chain data and the private calculated state. Okay, I think we've gone through everything, so let's go ahead and check out our next commit and see what happened, see what we changed. Okay, so in this commit over here on the far right, you can see we're only going to be touching a couple of files, right? We're only going to touch the updates file, and here are the changes we're going to look at in to the left in just a minute. We're going to look at the on-chain, so what the public state is. We're going to look at the private, the calculated state or the private state. We're gonna briefly consider those ordered operate, how to order them, and then we're gonna add one file called a task record, and we'll mention what that is in just a moment. Okay. So I like to start when we're dealing with the schema. If we recall previously, this was just an empty class, and so for our little to-do application, I'm just going to track a really simple thing of just a map or a dictionary or a hash map. And in the on-chain state, I'm going to have a single field called active tasks. And that active task is going to be a dictionary or a map of a string to a thing I'm going to call a task record. And a task record is exactly what you might think it is. It's just the individual, columns of the data that represent a single task. So task record is just going to be a few fields, and these fields were chosen purely for the sake of illustration. There's very little limitation in terms of what you can do here. So here, what I'm going to do is I'm going to actually copy that unique ID into the record itself, as well as I'm going to record the ordinal when this record was created. I'm also going to record ordinals about when this record is updated. And the reason we're using ordinals here is for determinism. We can't just use the time, because remember, in this distributed metagraph system, each node might run this thing or this operation that creates a task record at different times. And so the way that we can do deterministic time or deterministic steps in time is by using ordinals instead, because ordinal, all the nodes in the metagraph will agree on. I will, however, record the due date when I want this task to be due in epoch milliseconds. So I'm just going to use a long for that. And then I'm also going to have a reporter, so similar to like kind of Jira inspired here. And so then we're also going to define a task status. And so these might be equivalent to like, the Kanban columns. Task status is just going to be an algebraic data type, which has a couple different members. We're going to say different statuses are going to be backlog or in progress or in review or complete and closed. Then we're going to tie our different stages or the different transactions, the modifications to these task records to different statuses. And so remember, our on-chain state is just a mapping of that ID string to a task record. And then so our genesis is just going to be an empty map, right? We're not going to put any records in the state at first. Whereas our calculated state is very similar, except that this time we're just going to store the history of tasks. So on-chain state is the active tasks, so which tasks are either in backlog or in progress or in review. And then anything that's in complete or closed will move to the history, right? This way, our state, our on-chain state, doesn't just only grow in time. It can actually shrink. It can grow and shrink. Now, this history will be only growing in time in the simple implementation we have now. But you could, the flexibility of the system is such that you could decide to delete things from history given the business logic of whatever your application may be. But here we're just going to do something simple where things that are either closed or complete will go in history, and anything else in backlog, in progress, or in review will be considered active. And then just like on chain, our Genesis calculated state is just going to be a single empty map. So once we've decided on kind of the structure of our state, both the public state and the private state, the next thing that comes to mind are our updates. What are the things we're actually going to do to how are we going to modify these records over time? And so you might see here that I've expanded this to-do update is no longer a simple class. It's an abstract class, so that I can have different subtypes of it down here. And so we're going to consider 4 different. Here, let me just. Oh, I didn't. Never mind. Didn't do what I wanted to do. We're just going to consider 4 different tasks. We'll have a create task, a modify task, a complete task, and a remove task. The application that I'm envisioning here is that we will create new records by first sending a create task, and then we will progress that task through, from backlog to in progress to in review will happen through the modify task. And then whenever we want to complete something and we want to mark it as complete according to the status here, right? So you see we have a complete and a closed. So to complete something, we will send a complete update, but maybe in an agile type environment, sometimes things change or something goes stale or something's no longer applicable. So we might just want to remove a previous task entirely. And so we'll also have a way to remove tasks, and that will mark them as closed. So we're going to make a distinction between things that were completed, which went through the entire life cycle, and things that were closed, so like aborted, right? Tasks that were aborted. Okay, the last thing we haven't talked about yet is these ordered operations. And the ordered operation implementation here is simply to, in a block, we might have several types of updates that get sent by users. And so we're just going to group updates as into like tasks, or like updates, I mean. So all the create updates will be grouped together in a block or in a snapshot. All the modifies will be grouped together, completes together, and they'll be done in this order. So just to fully go over all the code that we modified within our little example. Okay, so that goes over step 2. So we're kind of done with our schema design. And so now that we have an idea of what our state is going to be, or what our tables are, and we have an idea of how we're going to modify those tables over time, the next thing we need to look at is how do we accumulate, how do we take those modifications and actually turn them into updates in the tables? So how do we combine updates? So we'll go ahead and check out the next commit. And stay here for a second. We'll see we're just going to touch 3 different files this time. In the task record, we're just going to add a simple method to help generate IDs. In the ML0 method, we're actually going to connect to our combiner function, and we'll spend a majority of our time talking about this actual implementation down here for the state update combiner. So let's go ahead and jump in. And let's look at the state update combiner. So if you remember before, this is just a couple of check marks, or I'm sorry, a couple of question marks. And now I replaced it with this simple pattern match. And the simple pattern match just routes to these 4 functions down here. And you see if we have a create task, then I'm going to call the service function aptly named create task, and I'm going to pull the state and the context So the context is some enrichment of the L0 node that's available from the ML0 service. And we can just hop to it really quick. It's actually all the way, it's given to us from tessellation. So, it's part of the innards of the whole Metagraph framework. And so that's a very simple API between the L1 node context and the L0 node context. So that's just to point out what that is. So we're going to take in the state update combiner, we are given a signed transaction, right? So a signed to-do update. We're given the state, right? So the entire data state, the public part and the private part. And we're given this L0 node context. And we're going to use all three of them in this create task. So to create a task, we're going to do, it's exactly what we might think it is. Where we need to create an instance of a record, right, which we're going to do here. And then we're going to inject that record into the on-chain state, right? So because it's creation, we're going to default it to be in the backlog. And backlog means it's an active task. And so we will leave the calculated state unchanged. So whatever the input state is, we're just going to extract the calculated state from it and just output that into the final data state that we return from this function. And the on-chain, but we will modify the on-chain state by, this is using something called a lens, which is particular to some Scala-esque things. But they're kind of easy to use. All we have to do is first focus on the inner table, the active task, or the inner field active tasks. And then we tell the lens that we want to modify that active tasks. And we're going to modify the map in active tasks by updating it. And we're going to update it with the ID of the task and the new record value that we created. And so I know I'm working backwards, but functional programming kind of, my opinion, works best understood kind of reading it backwards. So then the question is, where does this ID and record come from? And we see that the task record is really just built up. It's actually manually built up by taking the ID, which is generated, which we generate here, and that is purely a decision on my part to auto generate an ID. We could in our update require an ID to be sent along, but I decided to generate one whenever a transaction is received instead of having the user do it on their side. And so we see, if we look at the updates again, whereas modify task and complete task and remove task, all three of them have an ID field that requires to target a field in the state. The create task does not have an ID. And that's, like I said, simply because I made the decision to generate an ID on receipt of a create task. And so I placed that ID function in an object connected to task record. And so if you're more familiar with Java, you might consider this method a static method of the task record. And so it's a pretty simple thing that takes a create task and just hashes it. It hashes the JSON value of it and returns that value as a string. And so that's a side effecting operation. So that's why it's wrapped in an F here. But that's how we generate the ID. So we see that's how we get our ID here. And then we're going to get our current ordinal, and we get that, we fill in the current ordinal, which is if you recall, this is our creation ordinal and our last updated ordinal, which in this case are the same. So this is the ordinal at which this operation should apply to. And then finally, for the last few things, we are just turning our due date into a long, and as well as we're providing we're optionally getting the status from the update, but the update is, if this op status is an option, so it may be a none. The user may not provide one. So if they do not provide one, then we default our status into the backlog. And then finally, our reporter is just going to be the head signature on the transaction. So we could potentially have many signatures on a transaction, but there needs to be at least one. And so whatever the head transaction is, we're going to consider that as our reporter, and that's what we're going to use as the address that signifies who reported this operation, or who reported this new task, who's creating it. Okay, and that's everything about how we take a task record, right? And so we've kind of gone through how you get all those things. So now we've seen how we're going to do to create a new task. So pretty similarly, when we get a modified task, kind of working backwards, we return a data state, which is the new on-chain and the new calculated state. Again, a modified task is only progressing from either backlog to in progress or in progress to in review. So it will not modify the calculated state, since the calculated state only accounts for the completed or closed tasks. So we are going to modify our active tasks. So again, we just focus in on the active tasks, and then we modify that map by updating it with the ID that's included in our update and the new record that we modified. And so that new record is going to be here, and it's actually just a new instance that's based on the previous record. So you can kind of already tell that we're making some assumptions about this data, right? And so that's what leads us to the validations, right? We're just going to assume, for the sake of this function, that a previous record must exist, right? We're not going to enforce that it exists here or handle the case that it doesn't exist here. We're just going to assume that it does exist. And later, or in the next step in the tutorial, we're gonna see how to define such that this thing should never get into a failure state by rejecting validations, or rejecting updates that fail the validation that a record must exist. That way, our combiner function is always guaranteed to complete and not error out. So anyway, so assuming that making the assumption that an active task does exist. So here we will pull that active task, or that previous record, from the active tasks, and then we're just going to make a copy of that record, and we're going to update the last updated ordinal with the current ordinal, which is gotten similarly to how we got it before. And then we're going to change its status optionally to the optional value that's in the update, in the modification task, or we're just going to keep the previous status, right? And lastly, we'll also allow for updating the due date, right? And that's simply because that's our definition of how a modify task. It only allows us to, so we require that there's an ID to identify a previous record, or to identify a record, and then we'll optionally allow a user to update either the status or the due or the due date, right? And if they don't provide either, we'll just use the value that was previously on the record. Okay, so for our complete task, we'll start again from the bottom. So we return our data state. That's a modification of the on-chain and the calculated. In this case, we are going to modify the calculated, because now when we complete a task, we need to put it into the calculated state. And so we'll do that by focusing, getting the history field, and then modifying that history field with the new record, just like we've done before. But unlike before, we will remove, for the on-chain state, we're going to remove that old value from the record, or the old record from the map. So we can do that by focusing here, modifying it, and then removing this particular field. And then these other steps going back up are very similar to what we've done before. We just pull the previous record by assuming that it exists, and then we're going to copy it. We're going to update the last updated ordinal with whatever the current ordinal is, and then we're going to change this task status to complete. And then very similarly, for a remove task, we're going to do the same thing. We're going to put the new task into the history. We're going to remove that task from the on-chain state. We're going to pull the previous record from the active tasks. We're going to update it with the current ordinal. We're going to change the status to closed. And that's it. That's our whole combiner. That's our entire business logic for the 4 different types of tasks and how they modify the on-chain and calculated state. So once we've defined all these methods in this insert function, then we can jump to our ML0 service, and we see, if we scroll back down, we see that our combine function, we no longer have our little question marks down here. We have a state.insert, and we're going to do our updates to a sorted set, and then we're going to use the combiner. And this combiner here is actually up here as an argument into the L0, the application L0 service, and it is made in the ML0 service here as a signed update reducer, right? That was one of those fancy things over here from the right that I said we can just take as a given. That kind of provides just a really nice nice quality of life way to allow us to just do a state.insert, and then we give it a sorted list of updates, and then we say use this combiner, where the actual functions that are used to do the combinations are defined through this method we just talked about. Okay, so that's our combiner function. So like I said, the next step is for us to think about some of these rules that we have been defining. And so those rules are going to be, we're going to look at here. And we're just going to have a single file that we're going to look at in this one. And so let's just hop right to it. And so our validator rules. And so our validator rules are, and let's collapse it. And then I'm just going to, so we can look at it in a little bit simpler form. So the rules are, I tried to give them descriptive names. So, we've already encountered some of them, right? For a modify task, a complete task, and a remove task, we need to have a validation that ensures that the tasks exist in state, right? We don't want to start processing an update, a data update, or a task update that tries to reference a record that does not exist, because then our combiner function would fail. And so we can create a rule that ensures that the task exists that's applied before the combiner function is run. That way we know the combiner function won't error out, right? And we can do that pretty simply here by saying that, given an ID, which is a string, and given an on-chain state, right, we can just say state.actTask contains ID, right? So this is our test. We're gonna check that the active task contains that ID. And then this extra part here, this validated connect thing, is kind of just a fancy type thing for helping us do things. But you can really think of this inner argument to it as like a ternary if you're familiar with JavaScript. Here is your test, right? This is your conditional test. And then this is the value if true. And then this is the value if false, right? And then the thing that makes it a conditional validated is this validated connect thing. So the important bit here being that, we have your conditional test, and the error that's returned if it does not exist, we can define down here. and just record does not exist. It needs to inherit from this data application validation error, but then you can write whatever message is most useful to you as the application developer here. Similarly, kind of symmetrically, for the create task, we don't want to overwrite a task that already exists. So I'm also going to enforce that for create tasks, that I'm going to have a test that makes sure a task does not exist in active tasks. So it's basically the same test. The state active task contains ID, except I negate it with a not. And then some other validations that I'm just going to apply are things like the due date must be in the future. And so this is purely an application. I did this one to demonstrate that whenever a transaction comes in, the due date must be at least 1 hour from now. Now, remember that now can be slightly different between nodes while this is being processed. So this might not be the most rigorous test, which is why I gave it the 1 hour window, because snapshots should be created roughly every 5 seconds or so. So this by saying that a due date, it must be at least 1 hour in the future, lets us ensure that all the nodes agree that a transaction will be valid. But anytime if you're going to use, if you do anything with this, with the clock or pulling the system time in your metagraphs, you have to be very careful. And then lastly, I'm going to another like application level task or application level decision that I've made is I'm just going to say that given a modify task, that a modify task cannot have, if it does have a status, if there's some status inside the modify task, right? If there's no status, return the true value, return this parentheses as a valid. So say it's valid. But if there's no, or I'm sorry, if there is a task, if there is some status in this update, then check that that status is not complete or closed. If it is complete, then I'm going to return this error, or if it's closed, I return the same error. I just say invalid status for modify. Or if it's anything else, which is either backlog or in progress or in review, then we're just going to return a valid neck. And that's it. Those are the only 4 rules we're going to define for our little application here. And then we haven't yet defined, we haven't combined them yet to apply them to the individual things, right? Here, just the separable like rules. And now the next thing we need to do is actually apply those rules to our updates. So to do that, go ahead and we'll check out our next commit. So what are the update validations? And you see here that we're gonna touch 4 files. So we're gonna touch the data L1 validator, which is gonna do something very similar to what we did before, where we're gonna define kind of a router. So we're gonna pattern match, and we're gonna have the service functions below, which we'll go through. We'll do the same thing for the ML0 validator. And then we'll go to the ML0 service, and we're gonna implement the validator. So very simple, it's very similar to the combiner function where we just did state insert. Here we'll do state verify, and in the data L1, it's a little more cumbersome given but it's essentially the same thing. We'll do validator verify here, and then we have a little bit of wrapper to actually pull the state for us. But let's go ahead and look at the code here. All right, so we have our 4 validator rules that we just looked at. Whoops. So due date in future, task does not exist, task does exist and has valid status. And let's first look at the data L1 validator. And so the data L1 validator, so our verify function, remember this is where our question marks were before. So here we'll say, given an update task, we'll call the create task, or given a modify, we'll call modify. We're going to look at our create task. And so remember the rules that we needed to apply for the create task. So we're going to need the ID, right? Because we want to check that it does not exist. So we're going to go ahead and generate the ID for the task. And then the two rules that we're going to apply are due date in future. So when you have a create task, is its due date at least 1 hour in the future? And does the task not exist? So you're not overriding a previous task, right? And so those are referencing the validator rules from the independent separable rules that we previously went over in the last step. And then once we have each one of those steps done, we will combine them into a single list, and we'll do a combine all to zip it all up and return the whole thing. The way validated works is that it will show us if both of these fail, it will show us the error that both of them failed via this combine all. So then moving on to the modify task, given the modify task update, then we are going to check, or we're going to test three things, right? So we're going to check that if there is a due date, so some new date, is that due date at least 1 hour in the future? If there's none, then we're just going to return the valid, the parentheses as a valid neck. And then the other test we're going to do is that the task does exist. So the task must be in the active state, and that the modified task has a valid status. And so these three tests are then combined and returned as a single return value. Just for completeness, we'll go in and do the complete task. And so you see there's a bit of a different structure between these things. And that's because the modify tasks, this operation is a side affecting operation because the due date in future uses the clock, right? It returns this F thing, whereas these other ones just they don't return an F data validation. And so that just means that this pulling the system time is a side affecting operation. So that's why we have to use a for comprehension here, or equivalently, you could use a flat map. Since the complete task only needs to check that the task exists, then we can do our definition a little more simply by just wrapping the single test in a validator, and we don't need to have the separate we don't need to count for the side affecting operation. But this is essentially the exact same operations here, where we just do this one test as task does not exist, and then we return that. And then lastly, the remove task is exactly like the complete task. We're just going to check that the task does not exist. So that's it for the data L1 validator. And now for the ML0 validator, I actually just applied the exact same set of rules. And that was purely for ease of use of this example. The major difference in this case is that I do have a more rich context, so I could apply a more thorough evaluation if for some reason my application demanded that of me. So I have the ability to, in the ML0 validator, use the calculated state in order to evaluate tasks or the updates, but I chose in this simple example not to. And so the create task and the modify task, these are just a copy of the same functions. But I've duplicated them here just because I like to make them separable in order to account for the fact that I do have a more rich context to evaluate for this whole operation. So then now that we've got our validators defined, we need to connect them to our data L1 service and our ML0 service. And so for the data L1 service, as we saw a second ago, we need to get the on-chain state, and then we're going to apply that on-chain state using the validator.verify function. Yes, because this validator, there we go. This validator here is a data L1 validator, and that is created up here in the make function. Similarly, the ML0 or in the ML0 service, we will connect our verifier to the validator we just defined via this latest update validator here, which is defined by that ML0 validator as we defined here, or as we just explored here. So the it's a little nicer to look at. It's just state.verify with the state being the entire data state and the updates being the non-empty list of signed updates. And that's it. That's it for your validations and combiners. And so once you've done that, again, you've kind of got the whole ball game. You've pretty much defined your metagraph, and you can get going. So just to kind of fulfill what I promised you I'd do in the beginning, we'll just kind of quickly look at what how to define some custom routes. And so to do that, we'll look at the data L1 custom routes. And so we're going to change from this empty here and just use the structure of HTTP4S, which is the HTTP library that we use. We can define a simple get method, and then the path starting from the root, which is going to be, at IP address : port / data application. That's all in root. And then we'll have current time. And so current time will connect to this really simple operation that will pull the current time and return it as a JSON to us. And then we can also connect to some of those enrichment functions that we talked about, or I showed earlier, using the context with this get on-chain state and get latest global state. And we can make different paths and get functions here. And then we can also, sorry. So for this data L1, let's actually jump to the code. The data L1 custom routes, you see we have a method, so a way to get active tasks. So, given the context, which is an L1 node context, we can get the on-chain state from the L1 node context, and then we can just pull the active tasks and then turn that to a list, and then send that to the prepare the response to send back to the user. And so this method gives us a way to query the on-chain state and just dump the entire table to the user on request. Similarly, for the ML0 custom routes, we can do the same thing, just with the L0 node context. We go ahead and get the on-chain state, and then we do the same thing. We can just pull the active tasks. But since we also have access to the calculated state, not via the L0 node context, but as an argument passed into creating an instance of this ML0 custom routes, we can pull the history and turn that into a list and send that to the user, like dumping the calculated state table. And then just to point out that checkpoint service is updated here, is provided as an argument into the ML0 custom routes. If we jump to the ML0 service, and then down here at routes and ML0 custom service, we have that checkpoint service, and that checkpoint service is an argument into this function, and that checkpoint service was created up here in the original make function. And so that's how you get access to it. But those custom routes let us dump the tables to the user, just so you have a really simple way to query it, as well as the ability to get the last currency snapshot, and you could even count the updates in the snapshot as certain ordinal. And the ability to create many different types of custom routes is pretty handy at this point. Okay, and then lastly, let's go ahead and look at the daemons and application config. And so for the daemons, actually, it's pretty simple. We're just going to go look at the metagraph. We only have two functions we're going to modify, or two files. So we see that we're just going to add into our original main function, our entry point into the application, we're just going to spawn a new thread, right? And we're going to do that by creating a function called make periodic daemon, and we're going to use the periodic daemon provided by the tessellation infrastructure, right? And so here we have a way to just spawn a daemon or spawn a daemon that awakes every so often. And if we go back, then the thing we're going to have this daemon do, so this first argument that we provide to the daemon is its operation. And so for our little simple example, we're just going to log, we're going to provide a logging message that just says hello from the scheduler. And we're going to tell it to do that every 15 seconds. Alternatively, maybe you want a daemon that is configurable, right? Maybe you want it to read some files from an application config, right? So here we're going to do the same thing because we're going to take a config as an argument. We're going to call the periodic daemon again, but this time we're going to pull a message from our config file, and we're going to say that the daemon's idle time is determined in the config. And so our application config, we use a library called, or this example uses a library called pure config, but there's flexibility to do many different types of configuration libraries within the Metagraph. And so here you see in our ML0 daemon class, we just have a simple thing that lets us define a message and an idle time. And so then if we jump here to application conf under resources, you can see our default values for that ML0 daemon config are the message being howdy from a configurable daemon, and idle time is 25 seconds. And so this would provide you a way to, once you've built the application, you could come in and update this. You could also include functions to point to external configs. And so in this way, modify the config over time to be able to have your daemons do different things. The last things we're going to do is we're just going to see how it all works. So we're going to go in this and do some of this testing. So here I've already built a version of this application for us. So let's go ahead and using the Euclid build environment, which we covered in a previous video in the series. I'm just going to go ahead and start our operations, or start the whole to-do metagraph. And so when this comes back, we'll check in with it. And we're back. So now that we've gotten our metagraph spun up, we see all the different URLs that are that we have up. So let's go ahead and jump to one of these. Let's go there. Okay. And so now we're going to go to localhost 9400, and so this is the data L1 on a Metagraph node 1, and we're going to query the active tasks. So we expect this to be empty, and indeed it's empty. But let's make sure that it's working. So we'll go ahead and okay, and there we go. So we do have some data there, and let's make sure this ordinal progresses. There we go. So now we're at ordinal 8. Okay. So it seems like things are working. And this should be the currency snapshot. Okay, so it's on ordinal 3. Great. So our application seems to be up. So let's go ahead and query the ML0, and we're also going to query the active tasks, and we should see it's empty. And finally, we'll query the archive on the ML0, and it is also empty. Great. So we can see, or we can, do some simple gets here to get data from our application. We also have the Postman example or the Postman collection that's included within the example. And so we can go ahead and make sure it's working. Okay. So we can get the active tasks. We can get the current time, as well as the Metagraph snapshot. There we go. Let's jump down to the ML0 and ensure it's working. Okay, great. So everything seems to be working there. And so now let's go ahead and modify some stuff. Let's go ahead and generate a new task. So we're going to say this is a task description for July 26. And we're going to keep the optional status empty, and we'll set the due date. Let's actually set the due date to be, this is supposed to be 1 day in millis. And so this is, 1,000 milliseconds per second, 60 seconds per minute, 60 minutes per hour. We're going to say 1.5 hours. And then we're just doing 1, but I had been doing this in days before. So this had been 24. But if this is the hours, let's set this to 0.5. And now what we should expect to see is an error response. And there we go. So task due date in past, right? And that's because we set that the hour portion of this little thing, we set it to half an hour. So this is only 30 minutes in the future, which is not enough time. So instead, let's set it to be 24 hours in the future. Actually make this 1 day in millis. And we'll go ahead and send again. And there we go. So we got a valid response. And let's go ahead and go back to Postman. And we'll query the active tasks. And there we go. So we have our this is our ID. And it was created at ordinal 8. It was last updated at ordinal 8. Because we didn't provide a backlog, or we didn't provide a status, it defaulted to be in the backlog, like we expected. And this is the address that we sent it from. So great. So everything seems to be working. So let's go ahead and copy this ID. And now we will go to modify, and we're going to update it. And let's say in progress. And we'll go ahead and do a modify this time. Okay, so we got a response as we expected. Okay, so let's go ahead and look at the active state now, and voila, we see the task go to in progress. Okay, so now let's go ahead and do this and change this to in review, like that. And we can call it a modify again. And again, we get our task due date and pass. We can also say complete, and we can, so now we should expect to see 2 errors. And so there we go. So invalid status for modify and task due date and passed. So both of those reasons failed. So let's go ahead and make it valid again. So we'll do in review, and then we'll comment that out. We'll go ahead and actually modify this time. All right. Now we'll go back. So last time we queried it was in progress. So let's check what it is now. Okay. So now we've got our statuses updated to in review. All right. And now let's go ahead and let's complete it. So we'll go ahead and do that. And we'll go to complete. All right, we got a valid response. We'll go here. Okay, and so for our active tasks, we should be empty again when we look at it. So is that the case? Look at that, voila, empty. But our archive tasks, our archive table should have it. Hey, look at that. So our task is now complete. It was last updated in ordinal 18. It had been originally created in ordinal 8, and all the original information is still there. Yeah, so let's go ahead and try to remove that same task. And this should provide an error because it's no longer in there, right? So record does not exist as expected because it's not in the active tasks. But just for the sake of completeness, let's go ahead and show that we can go straight into in progress. We can make it a day in the future. Let's go ahead and save that. And we'll create a new task. So we create, let's jump back to Postman. We'll double check that we have a task in create. Okay. Just for the sake of showing multiple tasks, let's go ahead and do this again. So we should have 2 different tasks now. Okay, so we got 1 task, and then we'll. All right. So now we see we have the task we just created in the backlog because we had commented out and it was created in ordinal 24, and then we have the one we created a second ago that at ordinal 21 where we directly put it into the in progress column. But let's go ahead and for this case, I want to go ahead and remove it. Let's say that was an error. Or let's just I say error, like that was a mistake to have done that. So we're going to go and remove it. All right, so it looks like it went through. We go back. We'll look at active task one more time. Back to C1. There we go. Okay, so we have the task that was created at ordinal 24. And then we go back to archive tasks, and now we expect C2. And look at that. We have our original one that was complete at ordinal 18. And then we have this new one that's closed because we removed it. And that was done at ordinal 27. And so everything seems to be working as expected.
All right. Well, that about wraps it up. I hope this tutorial today has been of use to you. And if there are any questions or anything that was unclear, feel free to reach out to us on at the email here or on the Discord, or we really want to engage. And if there's anything that it's unclear, we're happy to be of as much help as we can. All right. Thank you very much.